Okay, think about this. Almost every single day, millions of us step into an elevator without giving it a second thought. But behind that simple ride is this hidden world of incredible engineering, a constant, invisible battle against immense physical forces. We're going to pull back the curtain and see the science that keeps us all safe. So that's the big question, right? How do engineers guarantee that a box weighing thousands of pounds, just hanging there, stories up in the air, is somehow one of the safest ways to travel? Well, the answer is all in the math, in mastering the unseen forces at the very heart of the machine. To really get the safety side of things, we first have to understand the system itself. And for a whole lot of elevators, especially in those low to mid-rise buildings, that system is hydraulic. And you should think of it less like a machine and more like a powerful, almost living system. I love this metaphor. It's actually from engineering documents by specialists in the field, like Noven Puya Lift, and it is the perfect way to picture it. The power unit is the beating heart, and all the pipes are the vital arteries. It just pumps fluid, the lifeblood of the whole operation, to create movement. It's a really simple, elegant, and incredibly powerful idea. So, what are the actual pieces that make up this system? Well, if you want to engineer for absolute, foolproof safety, you have to master every single component, because a failure in any one little part could compromise the entire thing. These are the key players right here. You've got the jack, which does the actual heavy lifting. Then there's the power unit, which is the muscle. The piping carries all that force. The valves, they're kind of like the brain, controlling everything. And of course, the hydraulic fluid itself. The safety of that entire elevator literally hangs on how precisely each and every one of these parts is designed. And right at the center of it all is the hydraulic jack. This is where the real work happens. You see, pressurized fluid pushes a piston up, and boom, the elevator rises. It sounds so simple, right? But containing that insane amount of pressure and making absolutely sure that piston never fails, well, that is a huge engineering challenge. And that brings us to the first massive problem engineers have to solve: containment. The system is using pressures strong enough to lift tons. So how on earth do you build a container that can handle that kind of force? Not just one time, but thousands of times a day for decades on end. You know, it really all boils down to one single critical calculation. Get this number wrong, and you're looking at a potential catastrophe. But get it right, and you've built a system that is fundamentally, unshakably safe. Okay, to get that magic number, engineers use what's called a hoop stress calculation, and it depends on these four things. You've got P max, which is the absolute maximum pressure the system will ever see. Then DC, the cylinder's inner diameter, because the wider it is, the more total force is pushing out on the walls. Sigma allowable, that's just the tested strength of the steel itself. And finally, C, a crucial little extra safety margin for stuff like corrosion over many, many years. And that's the whole point right there. This calculation isn't just about making sure it doesn't burst on day one. No, it's about making sure the structure is so tough, so robust that it can handle the stress of daily use for the entire lifetime of the elevator. But containing pressure, that's only half the battle. There's another threat, one that's a little quieter, a little more insidious, that engineers have to defeat: buckling. The best way to picture this, imagine pushing down on an empty soda can. At first, it's fine, it resists, but then, all of a sudden, it just crumples sideways. That's buckling. And an elevator's piston? Well, it's basically a very long, very thin column under an immense amount of pressure, which makes it a prime candidate for exactly this type of failure. This comparison makes it super clear. A short, thick rod is incredibly strong, but a long, thin one, like an elevator piston that has to extend up several floors, it just wants to bend and fail sideways when you compress it. So the entire design of that piston, its diameter, its wall thickness, is all calculated specifically to make sure that can never, ever happen. And here's the thing, engineers don't just design it to be strong enough. They build in a massive safety factor. The piston has to be able to withstand at least double the maximum load it will ever face in the real world. This isn't just about meeting a standard. It's a deep, profound commitment to safety. But even with perfectly calculated cylinders and pistons, engineers are always planning for the unexpected. What if something goes wrong with the power unit and the pressure suddenly spikes? Well, that's where multiple, redundant layers of safety kick in. There are three totally separate lines of defense. First, you have your normal, everyday operating pressure.
Now, if something causes that pressure to spike, a pressure relief valve automatically opens up at 140% of that normal level, and it just bleeds off the excess. But what if that valve failed? Well, even then, the components themselves, the cylinder, the pipes, all the fittings, are built to withstand even higher pressures before they'd ever burst.
And just look at how huge those safety margins are. If normal operation is 100%, that first safety valve kicks in at 140. But the parts themselves won't even begin to approach their breaking point until at least 250% of that normal pressure. It's a system designed with layers upon layers of protection.
So when you put it all together, what does it all add up to? It's really a philosophy. It's this deep understanding that in this kind of work, there is just zero room for error. Every single calculation, from wall thickness to buckling resistance, is another critical link in a long chain of safety. Ultimately, this is what it all comes down to. This statement is basically the golden rule for professionals in this industry, and it really says it all. The safety we just take for granted is never an accident. It is the direct result of meticulous, deliberate, and deeply responsible engineering. So, the next time you step inside an elevator, just take a second. Remember that the machine you're in is this quiet monument to unseen science. It's a testament to the engineers who calculated every single possibility, all to make sure your journey from one floor to the next is and always will be perfectly and wonderfully uneventful.